really have no idea why they asked me to talk about the lessons from the space, because really, it's the lessons that have not been learned from the space industry, or by the space industry, or by us. We all know that we live and work in a capitalist system where we talk about the time value of money, but we mostly talk about cost, not about time. Very little discussion about time. But in a system, a capitalist system, where we are talking about the time value of money, time is a critical factor that is never discussed. So that's why we're going to go with this conversation. It's only a little bit about space, and it's mostly about mining and how mining also has to change. Unfortunately, one of my beliefs is that we cannot make mining equipment, mining trucks, bigger. We just can't. Therefore, we have to make them smaller. And we have to make them more effective at doing what they do by being smaller. But since I live and work in North America, nobody is interested in a smaller truck. And so that's just a fact of life. So that's not going to be a successful conversation to have. The place, however, that you might be able to persuade people to use smaller vehicles are those people who want to go to the moon and do things on the moon. Not because they want to use small vehicles on the moon. Some people actually do want to use giant machines on the moon, but that's too difficult to lift off from Earth. So the only machines that can go there are small. So here we are. This is what my organization does. We're the Center for Excellence in Mining Innovation, and we have the Mining Innovation and Commercialization Accelerator to move small, medium-sized enterprises through the valley of death into producing commercially viable products and services that can improve the performance of the mining industry. We have 6 little organizations across Canada to help us do that. And you can see the 4 themes that we have is to increase our productivity, reduce the amount of energy that we use autonomous equipment systems, and also reduce our environmental footprint by changing the way we manage tailings. We won't talk about tailings at all today. We're going to talk about the moon just to start with. Now, the problem with these pictures is they're all a fantasy. That cannot happen on the moon. It's simply not possible. You can see on the top right-hand corner this giant heavy lift rocket sitting on the lunar surface. The lunar surface is made out of dust. And the plume that would be driven by that huge rocket landing on the moon would probably go 350 kilometers in every direction, because the moon has no atmosphere to stop the dust from being blown 350 kilometers away. So no rocket like that could actually land on the moon and stay that way. It would probably create a huge crater of its own and then fall over. So complete fantasy. All of these other things are also a complete fantasy. And here's why. And also, the other thing is I'm only talking about the moon because it's the closest. Why? You remember that Elon Musk has been talking a great deal about going to Mars. I don't think he talks very much about that anymore. And the main reason, I think, is because the travel time to Mars is about 10 months. The travel time to the moon is 3 days. So if you can't make it work on the moon, why would you even think about trying to take it to Mars? You can't get there from here. Second of all, on the lunar surface, things that you and I on Earth call falling stars are actually pieces of rock. And because the moon doesn't have an atmosphere, those pieces of rock that fall from the sky on the moon don't burn up in the atmosphere because there isn't one. They just land with a clunk wherever they land. And if that's on your nice, cute little buildings on the surface, they're just going to puncture a hole in that system. Unless it's clad by very thick protective material, the micrometeorites will just break through and punch a hole in your building. Second of all, there's cosmic radiation constantly on the lunar surface, so it's a very unhealthy place to be. And then you have the temperature variations, which are severe. Far, far more severe than going from Canada, where right now in my hometown in Canada, the temperature is minus 21 degrees, In the summertime here, it would be well over 40 degrees here. That is a minute temperature change compared to the moon. And why? That's the unstable dust there. Here's why. The operating time on the surface of the moon is about 4 hours every 28 days, because nobody could tolerate standing on the lunar surface for any longer than that. And here's why. Because the daytime temperature, and daytime on the moon, is 14 days in a row of continuous sunlight. And the temperature during the daytime is 120 degrees centigrade. So nobody wants to work on the surface of the moon for 14 days in a row in 120 degrees centigrade, second of all. And the nighttime temperature, I'm sorry, I said 230 degrees, it's minus 230 degrees. So the temperature between daytime and nighttime on the surface of the moon changes 350 degrees, from plus 120 to minus 230. So nobody is driving a rover on the surface of the moon ever for more than an hour and a half. You've seen the movies like I have seen of the moonwalks. Every moonwalk you have ever seen on the surface of the moon happens at twilight or dusk. And that happens every 14 days. And the reason for that is because every hour and a half is the length of time you have that the temperature on the surface of the moon is actually humanly tolerable, in between 120 and minus 230. So none of that is ever going to happen on the surface of the moon. So let's leave the moon behind for a little while and talk about underground mines, which is where I started my career 40 years ago. You see this little machine on the top left. I used to operate one of those machines for about 3 weeks. I was very happy to leave it to my colleagues to continue working with this machine, because I still had all my fingers and my head on my shoulders, because this machine can take your head right off. And it did for many, many people, just not me. So I was happy to see that when we changed over in 1985 to the machine on the right-hand side, that's the big LHD. And the problem with that machine is that about 90% of the time we're moving the equipment and we're moving the material in the bucket, but the pile of ore that we spent hundreds of thousands of dollars to create is not touched for more than 10% of the day. That pile remains there, and it's a simple calculation. I don't do AI, I have no algorithms. My technique is called arithmetic. And if I dig into the muck pile with my LHD for 30 seconds, and I drive 2 minutes to the dump, spend 30 seconds to dump, and come back again, that total cycle time is 5 minutes. And out of the 5 minutes, the pile remained untouched by any piece of equipment for 4.5 minutes out of 5 minutes. The task here is not to move the machine. The task is to move the pile. But the pile is not being moved 90% of the time. We are moving the machine, and it's really great to see that, and you'll listen to equipment operators who say that the most important thing is the utilization of the equipment. No, it's not. The most important thing in a mining operation is the utilization of the ore. That's your job, is to move the pile, not to move the machine. So, this machine on the left uses 15% of the time to move the machine, and 85% of the time it's moving the payload. It's just moving the muck from the front of the machine to the back of the machine without moving the machine. And then when it's full, then you have to move. But the really important factor is this one. That machine weighs 1 ton, and it carries 4 tons. The machine on the right carries 10 tons, and the machine weighs 30 tons, and it comes back empty with another 30 tons. So for every 10 tons you move with the machine on the right, you move 60 tons of machine. And what that means is that 80% of the fuel that you burned in that machine was to move the machine, and 20% of the fuel that you burned in that trip was to move the product. So what you have to decide is, are you in the machine moving business, or are you in the product moving business? Because if you're in a really deep underground mine, you need to be in the product moving business and not be in the machine moving business. And for the last 40 years, this machine was developed in 1985, we have been in the machine moving business, and we're still in the machine moving business. And you would say, well, this is underground, it's not really relevant for big open pits, because, you know, it's different. Actually, no, it isn't. Here you can see rows and rows of trucks going back and forth. It is slightly different for the trucks, because the truck, the mass of the truck, is exactly the same as the material, the mass of the material in the back of the truck. But you can see on the left-hand side, there's all the empty trucks going back again on their own. So, in this case, it's not 80% of the fuel being used to move the truck. It's only 75% of the fuel to move the truck. And 25% of the fuel is being used to move your product. So what is your business? Is your business moving product, or is your business moving machines? Right now, we are firmly in the machine moving business, and we shouldn't be. Ore, like this, in any mining operation, is the lowest value density material in the entire industrial complex, because at every stage that ore is upgraded in value. If we're moving the lowest value density material with an expensive material moving system, we're losing money. And that's why, over the last 30 years, we have slowly been going out of business. It's just getting faster now, because we're deeper, and the mines are older, and the process of going out of business is accelerating. And there is an end point. And so, here you go from 75%, and I guess, and so we did a competition. On the left-hand side, you can see there's a NASA challenge in 2011, and our little university in Sudbury won that competition in 2011. And in 2011, because this small Canadian university won the NASA competition for MIT, Stanford, all the big universities in the States, NASA, for the next 11 years, did not allow non-US universities to compete in the competition. Therefore, for 11 years in a row, only American universities could win the competition. They changed it again in 2022, and again, our little university in Sudbury went back into the competition. The competition was to move 10 meters, move regolith 10 meters lateral and 3 meters vertically, and move 10 kilos in an hour. None of the other 6 finalists managed to move 10 kilos in an hour. Our little university was able to move 10 kilos, and they moved the 10 kilos in 11 minutes. Not in an hour, in 11 minutes, and they used an Archimedes screw to move the regolith. And that is technology from 265 BC. Not high-tech, no algorithms, no AI was involved in this process whatsoever. Simple arithmetic designed to say, this is the easiest way to move dust on the surface of the moon. And it is. Very low energy, very low mass, and very effective. So why is that relevant today? Because the Archimedes screw is also called a spiral conveyor. So it's a conveying system, but it's not a conveyor belt. It is a conveying system to move low-value material on the surface of the moon. So what we could have done, instead of making the change to this machine on the right, the top right, we could have moved to this machine, which is on the bottom right, because that is called a continuous loading machine. And when you see what it does is it's scraping the material into the jaws of the machine. Inside the machine there's a little steel conveyor, and that machine is moving product at 450 tons an hour. Now, the reason it's moving that material at that speed is only because the conveyor is actually only 0.8 of a meter wide. The machine is actually 2.3 meters wide. And the reason it's 2.3 meters wide is because it has a cab on the side, which means you can't make the machine more than 2 meters wide in the kind of drifts, the tunnels that we have in these mines. So the cab is forcing the conveyor to be small. You'll see how we can change that in the future. It's actually 3 times more ore at only 20% of the energy, because the only moving component in this machine on the bottom right is the small conveyor inside the body of the machine. So that is moving, the moving metal is about 25% of the mass of the product that's being moved. In the case of the top right, it is 6 times the mass of the material that's being moved. So that's why it's much more cost effective. And what you need to do then, if you're moving the material at 450 tons an hour, you just need to keep the material moving at 450 tons an hour. And if you make it completely autonomous, you can change it to do that, so there's no cab. You can make the conveyor wider, and now you can move 900 tons an hour very easily indeed, and that means you're now moving 18,000 tons per day rather than 3,000 tons per day. This is the difference between automation of the machines that we have now, like in the top right, versus automation. Automating the machine on the right, what you do in the red label there says you reduce the direct labor, because that is the operator that drives the vehicle. But the efficiency of the machine is exactly the same, the fuel consumption is exactly the same, the maintenance team, which is 2.5 times more expensive than the driver, the maintenance team is also exactly the same as it was before. Nothing else has changed. So you eliminate the driver, but you do not eliminate any of the other costs. If you go to automation, you change the design entirely, you eliminate the direct labor because nobody needs to drive it, you reduce the maintenance labor because the only maintenance labor is to change the conveyor, and finally, you increase the process efficiency. And so you end up with a system that is roughly 30 times more cost effective than the machine in the top right-hand corner. So why don't we do that? Because we've been very comfortable using trucks for the last 40 years, and nobody really wants to change if they don't have to change. And so we continue to use the systems that we use, and if we continue to do that, that's what we have to do. The reason I'm talking about this in terms of the mines is because I cannot sell that small machine on the right-hand side here to big mining companies. But I can sell the idea to people who want to do productivity on the moon. Because in order to get the machine off the surface of the Earth, it has to be very small and very light, and when it gets to the moon, we can make sure that it's very, very cost effective to do the work that needs to be done. So that's what we can do. We can actually make that work that way and make that happen. So here's where we have this we could have a completely autonomous, low-energy, modular design system. You have to protect people from the conditions that exist on the surface of the moon, because none of the photographs that you've seen about what happens on the moon can possibly happen. In exactly the same way as some of the sessions we were talking about this morning said, all we need to attract more investment to the copper mining business or the nickel mining business, all we need is a higher price for copper, and we'll get more investment. The reason we have the high demand for copper today is to electrify the economy. Electrifying the economy means producing technologies that use electricity that are less expensive than the technologies that use fossil fuels, because we're trying to displace some fossil fuel from the economy and replace it with electric technology. You cannot replace low-cost carbon technology with higher metal prices that produce higher electricity systems. Because right now, most of us in this room probably do not drive an electric car, because an electric car is much more expensive than a gasoline car. And if you make my electric car more expensive, with more expensive copper, I will be even less likely to buy an electric car, and so will everybody else. So higher prices for metals means we actually kill the demand for more metals. because nobody will make the transition to an electric economy, to a low-carbon economy, because this is not an open competition. We're competing against the cost of carbon and the impact that carbon has on our environment. And so that's the transition that we cannot make. What we actually have to have from the mining industry is we have to have much more copper at a lower price point. So we have to make copper cheaper than it is now, not more expensive, because if it's not cheaper than it is now, it will not outcompete the existing cost of carbon in fossil fuels. So this is not a free competition. This is a constrained competition in exactly the same way as when the Americans lost their competition, NASA lost their competition, they made it impossible for non-American schools to participate in the competition, so their team could always win. If we insist on trying to make copper and nickel and lithium more expensive, we will lose the competition with carbon. And that means the consequences that we currently see, and you've seen it on the news this week, massive fires in Los Angeles. We've also seen massive floods in Europe and other places. These are the impacts of climate change, because when you warm the atmosphere, you get more frequent and more severe climate events. That is our future if we do not electrify the economy. But we cannot do it with more expensive metals. If we want to have more metal and less expensive metals produced, you have to have innovation. And so that's what my little organization tries to do, and tries to develop the kinds of innovations that need to be developed and need to be adopted by mining companies. The problem is, in most countries of the world, they've been doing the mining the way we do it now for the last 30 or 40 years, and the mindset is the limiting factor. It's not the technology. We have 50 companies that we're supporting right now with $160 million, and they're all coming up with new and better ways of doing things, not just this example, but many other examples. But it's very difficult to get large mining companies to buy into the change, and so no change happens, and the people that operate inside the mining companies are much happier. One of the panelists this morning said, we have to incentivize mining companies to change the way they do things. Actually, they already have an incentive. If they continue to do things the way they do things now, we will have a supply-demand gap. And when there is a supply-demand gap, the prices go up. So the companies that are now producing copper and nickel, if they do nothing, the price for their product will go up, and their profits will go up, and the individual bonuses for the people in the companies will go up. So they already have an incentive not to change anything. That is the incentive that we have to defeat. And I don't know how to do that. I, in my little innovation center in Canada, have reconciled myself not to the idea that I can somehow change the global mining industry. I hope I would be able to make some changes here in the kingdom, but that remains to be seen. All I can do for the last phase of my career is to remove the excuses for doing no change at all. Many, many times in the last 10, 12, 15 years, I've heard executives say, I would really like to try this new idea, but actually, there is no technology for that. So it's a great idea, but there is no commercial technology I can buy to make that happen. So what we're engaged in now is making sure that these new ideas and new techniques are commercially available. And now the executives who've previously said, well, I'd love to make that change, but there is no commercial solution that I can buy, to make that no longer true. So at the least I have accomplished is to remove the excuses for making no change at all. And that, I'm afraid, is where the mining industry has been for the last 10 or 15 years. We can all see what's happening to the number of mines that are producing copper at an acceptable price, and things are still going in the wrong direction. We talk about electrifying the economy. That means the demand curve for copper is increasing, but the core production level, global production level of copper is at the peak in 2025. From the end of 2025, for the next 20 years, the capacity of the global copper mining industry reduces its capacity by almost 50%. And so you cannot electrify the economy with only 50% of the copper you're producing in 2025. That is the consequence of where we are, and it's the consequence of 20 years or so of underinvestment by mining companies in exploration and underinvestment in innovation to improve the productive capacity of the whole system. We can't continue with manual operation of batch processes. We have to move away from manual operation to autonomous and make it all electric. I have been to, and I know it's very popular to talk about ESG and the kinds of changes that could be contemplated, but ESG, the G, stands for governance. Governance is a policy issue for the board of directors or for the government, provincial or federal government. I have been to hundreds of local communities where the community has a problem with the local mining operation. And no community ever complained about the company policies or the government policies. What the communities complained about was lack of access to land, lack of access to water, lack of access to clean water, lack of access to clean air because of the toxic dust that's released from the tailings ponds. So these are physical, material changes that have to be made. Just changing your governing documents does not improve things for the local communities. So there's a big distinction between what happens in the board of directors meeting and the documents that you have in the corporate vault and what actually happens on the ground. And unless we start to change the outcomes for local communities, as you probably know, we see more and more resistance to new mines opening because nobody wants the negative consequences of the current mining practices. So all of the innovations that we focus on, not for the moon, of course, but just for everything that we do, is we're looking at technologies that actually people would consider to be obsolete because they're simple machines that are easily modularized and then can be easily have components replaced. So they're simple and effective. It's also low-risk innovation because the machines that we were talking about were being used 60 years ago. This is not a new machine. All we have done is change it from being driven by compressed air, pneumatic, to an electric motor. And instead of having some poor individual trying to drive the machine with 2 levers, you can make it completely autonomous and program the whole machine to do what it needs to do. Then it becomes much, much more effective in doing what it needs to do, and the whole system benefits. So, that really is it. I'm not going to finish off talking about the mine. I'm not quite sure why they wanted to have a presentation on space, but it is the model where the only people that might want small mining machines are people who want to move moon dust on the surface of the moon. The advantage I have is in doing that for the space industry, first of all, many more people are prepared to invest in small machines to go to the moon. I have no desire whatsoever to go to the moon. None. And I don't understand why anybody would. But if they're prepared to invest in the machines that we need as a prototype for the machines that we need on Earth, then it's a worthwhile exercise. And that's my only reason for being engaged in the mining space. I can say that safely because I know there's nobody here from the space industry at all. So nobody's going to hear me say that I don't care about the space and I don't care about going to the moon. I will be long dead before any of this happens. But if I can create the prototypes that we need to begin to change the way the mining industry operates on Earth and helps us make the energy transition that we know we have to make in order to combat climate change, then I'm happy to put in the effort to do that. And with that, I'll stop talking and let you ask any questions if you have any, or maybe you're just waiting for the next speaker to come. Oh yes, this is the summary really. Modern Earth model mining technology is massive, energy inefficient, and has huge teams of maintenance people. There are no maintenance people on the moon. We're not sending people to the moon to be maintaining the equipment. So that's not a model that we can use. The lunar surface is remote, hostile, and resource constrained. It's actually a worse place than northern Canada in the wintertime or in Saudi Arabia in the summertime. It's much, much worse than both of those places. And it happens every 14 days. So this is not a comfortable place to be. But we can make machines that are autonomous, modular, energy efficient. And the other thing I've learned about this is the lessons for mining in the future, and these are lessons that we have forgotten. We always knew them, but we've forgotten, is they're actually from the mining manually in the past. Number one, activity is not effectiveness. Just because we're moving machines doesn't mean we're being effective at the task at hand. The task is to move the product in a pile. Number two, continuous transport systems are 15 to 30 times more effective than batch systems. Maximize the energy to move the ore or rock product and minimize the energy you need for the equipment. Use time wisely. It is the only commodity you can never replace. You can get more money, you can spend more energy and effort, but you can never get more time. It's a completely wasted resource. And finally, the environment always wins. It always wins. You have to make the resources of the current environment work for you and not try to battle against those resources. So trying to do some of the things that we're trying to do on the moon will never work because the environment is not suitable for those kinds of technologies. So, just like we wouldn't want to have particular pieces of equipment in the middle of the desert, a camel is a very, very efficient machine for operating in the desert. It is absolutely the wrong machine for operating in northern Canada in the wintertime. So you have to gauge what is the environment we're in and how do we make our production systems conform to the constraints of the environment. Well, that's it. I'll stop talking and let you listen to the next speaker, my good friend, Dr. Tema Adajani. Here we go. Thank you.